All right, the clock turned 9 o'clock here in Colorado, so I think we can get started. See, we got 30 people so far, people coming in. So welcome everybody to the fifth seminar series for the DC-MUSE Consortium. Today, we're going to be talking about membrane-based processes for carbon capture and conversion. We have two absolutely outstanding speakers today, one from academia, one from industry. First, we'll be giving a talk from academia is Dr. Justin Bowie, who's currently an incoming assistant professor at NYU Tandon School of Engineering in the Department of Chemical Biomolecular Engineering. Will be starting next fall. Justin received his Ph.D. in chemical engineering at the University of California, Berkeley, working with Dr. Adam Weber and Professor Alexis Bell. He used continuum-level theory to understand the impacts of transport and catalysis in bipolar membranes, which we'll talk about today, with applications of CO2 reduction and now carbon capture and conversion. He's done postdoctoral work with Karthish Manthiram at Caltech and is currently a research fellow at MIT, working with Professor Coley and Professor Klavs Jensen. Our second speaker today comes from industry. It's Dr. Eowyn Lucas, who works at Captura, where she's a senior membrane and electrodialysis engineer. She, in her role there, plays a key role in advancing and scaling the company's membrane and electrodialysis technologies for carbon removal from seawater, which we'll be talking about today. Her background is her PhD. She got in material science from Caltech, where she worked with Harry Atwater, working on things related to her talk today on electrochemical CO2 capture. I'm Wilson Smith. I'm a professor of chemical engineering at University of Colorado Boulder. Nice to see everybody here. We're up to 50. These numbers keep climbing. So I won't take any more of your time and introduce our first speaker, Dr. Justin Bowie. Justin, the floor is yours.
Great. Thanks so much, Wilson, for the wonderful introduction. And it's really great to see so many people here and so interested in this topic of membrane-based processes for carbon capture. So today I'll be talking about some of the work that I did during my thesis at UC Berkeley on resolving the physics of bipolar membranes for carbon capture and conversion. And so whenever I give a talk on bipolar membranes, I think it's really nice to start by introducing an ion-conducting polymer, especially for maybe people in the audience who are here from a carbon capture or industrial chemistry background and haven't really seen these materials before. And so these materials, what I'm showing here is a cation exchange layer. And it's called a cation exchange layer because it's selective for the uptake and transport of cations. And the way that happens is these polymers contain hydrophobic backbones with hydrophilic side chains that contain negative fixed charge. Because you have negative fixed charge within the polymer will selectively reject other negative ions by electrostatic repulsion and allow for the selective uptake and transport of positive ions. This electrostatic repulsion is known as Tandon exclusion, and the ions then, the counter ions of opposite charge to the polymer can then transport selectively in the electrolyte channels in the polymer. This creates a polymer or material, a separated material that is selective only to the transport of positive charge rather than negative charge. If I take two of these types of materials, one that's positively charged and selectively transports anions, and one that's negatively charged and selectively transports cations, and I put them together, and then I add a catalyst layer in between the two membranes, one which facilitates the acceleration of reactions that can occur at this interface, I get a composite material, which I'll refer to throughout this talk as a bipolar membrane. And the thing that I think is really, really important, and I hope that you get out of this talk, is that these bipolar membranes possess some really nice emergent properties and functionality that make them much greater than the sum of their parts. And the really interesting and the most important functionality that these bipolar membranes possess is their ability to convert applied potential into gradients in pH. So if I take a bipolar membrane, this anion exchange layer, cation exchange layer, catalyst layer, composite, and I sandwich it in between two electrodes, and I make ionic contact between the electrode and the polymer with a liquid electrolyte, I can apply voltage across that membrane. I apply voltage across the membrane, I get a potential drop, electrostatic potential drop through the polymer that looks something like this, where because you have a lot of charge in the individual polymers, all of that electrostatic potential drop is screened at the interface between the two oppositely charged polymer layers. This creates a really large electric field, and that electric field is sufficient to drive chemistry at this interface when paired with this catalyst layer. And the biggest example of a reaction that you can drive at this interface is the dissociation of water into protons and hydroxides. So water at this interface under this large electric field will split into protons, hydroxides. The protons will go into the cation exchange layer because of the selectivity of the cation exchange layer for the proton. Hydroxides will go into the anion exchange layer. And this creates an increase in the pH of the anion exchange layer side and a subsequent decrease in pH of the cation exchange layer side. And this results in an overall pH gradient that is developed that is directly proportional to the amount of voltage that I've put into the system. And so this tells us that we can use a bipolar membrane to convert electrical energy into a gradient in pH. And there are a lot of interesting applications for this type of chemistry, but the most interesting one, at least from the perspective of industrial chemistry and carbon capture, is the ability to replace the industrial calcination reaction. So this calcination reaction is really important for carbon capture and also for a lot of industries like cement production. Essentially, you take a calcium carbonate solution and you burn it at very, very high temperatures using natural gas, and that allows you to liberate carbon dioxide from that calciner. This is really important because when we capture CO2, we often capture CO2 in the form of a carbonate, and then also in the production of cement, we have to take lime and convert it into cement clinker precursors, which involves this calcination reaction. We can use a bipolar membrane to basically circumvent this entire process, where instead of using this high temperature calciner, we can apply voltage and we can use acid to strip CO2 from our bicarbonate solution. And then we can use base to regenerate that carbon capture sorbent. And so we can basically use the bipolar membrane as a means to replace this high temperature reaction with a low temperature electrical process. And this has an energy cost that at the moment has not really, when we started my PhD, was not really well quantified. And so one of the goals for the project that I actually worked on quite extensively with AON was to try to understand the dynamics in these bipolar membranes for this electrochemical calcination, and then to quantify the energy losses and the mechanisms within that system. And so what we implemented as a means of really understanding these systems was a multi-physics simulation approach. And so the beauty of bipolar membranes is, there are these really nice mesoscale systems where you have sort of two membranes inside of a bulk solution. And there are all of these different phenomena that occur within these materials. You have the dissociation of water at the interface, the transport of water from the bulk electrolyte to the interface for dissociation. You have the transport of different ions that can go in and out of the membranes. And then also you have dynamic buffering reactions. So for instance, the conversions of bicarbonate to carbonate to CO2, all of that is happening out of equilibrium and dynamically within the polymer during any of these processes. So we need to find a way to basically understand how all of these processes interact within these systems. And one way to do that is by actually converting all of these processes into their governing equations that govern the physics of these systems, and then building a physics-based simulation to understand them. And so this results in a few very simple equations that chemical engineers will be very familiar with. And it's this conservation of charge, the conservation of mass, and then in the conservation of mass, an understanding of how the chemical potential informs the flux and the transport of these ions within the polymer. And then beyond the engineering equations, there's also a lot of chemistry that's happening. As I mentioned, you have all of these reactions that can occur within the polymers that are non-equilibrium and dynamic within the material. And so we can link all of these together. These buffer reactions appear in the source terms for our mass conservation. And then also these chemical potentials are influenced by the local electric fields and how these occur out of equilibrium. And also very non-ideal behaviors become very important. And so we can basically create a simulation that includes all this chemistry and all the physics of all these different ions and represented as a form of highly coupled nonlinear partial differential equations that we can solve to get basically a digital twin of the bipolar membrane that is operating in these carbon capture systems. And so one thing is, once we have a model, we have to find a way to validate it. And this is where working with a really good experimentalist like AON becomes really valuable. So AON had been testing these bipolar membrane systems for oceanic carbon capture and also for operation of these electrochemical calcination processes with seawater and also varying concentrations of carbonate. And what we were able to do was we were actually able to see how the current voltage characteristics of the bipolar membranes that she measured in these different carbon capture solutions compared to what our experiments predicted. And sort of the magical thing is you can see here that there's these very non-intuitive behaviors to these polarization curves. Typically, when we're running a bipolar membrane, we expect a very typical exponential takeoff on these curves. But what we see is we see these very interesting sort of hump behavior at about half a volt of applied potential across the membrane. So something that was really interesting, but it's also something that both the experiment and the model reproduce very faithfully, which to us was a pretty good sign that the physics of our model were representative of what was happening in Aowen's experiments with these membranes. And then once we had that understanding, we were also wanted to really understand what was happening within this region. And so what's really nice about a model is we can actually break down the current. So when you get an experimental result, you sort of don't know necessarily what's happening under the hood, but with a model, we can break down all of the contributions to the current density that are occurring within the system. We see that there's a very small amount of current associated with the crossover of coions to the system, which is good because this coion crossover is typically known as an inefficiency in these bipolar membrane systems. We see that there is actually a very non-negligible contribution of electric field or catalytically enhanced bicarbonate dissociation, which results in this first takeoff at about half a volt. So bicarbonate splitting into protons and carbonate. And then finally, we see the standard water dissociation takeoff that we expect. And so that basically tells us that this hump feature is actually due to a field enhanced bicarbonate dissociation that occurs at around half a volt, which is consistent with the pKa of that buffering acid. The other thing we can do is we are really interested in the energy efficiency of these systems. And so what we can do is we can then resolve the contributions to the applied voltage. So not just the contributions to the current density, contributions to the voltage. We can see that there's a lot of voltage or energy that's being put into this membrane to drive the system that is just purely thermodynamic. So it's unavoidable. If you're going to try to create a pH gradient across the system, there is a price that you have to pay to create that pH gradient. But you can see there's a lot of headspace above just the thermodynamic requirements for the pH drops. You see there's a lot of losses associated with the kinetic overpotential, so the energy required to drive the catalysis of water dissociation, as well as potential associated with losses due to the ohmics through each of our membranes. And then finally, we see an interesting and non-negligible loss associated with the coverage of bubbles on our membrane. The last thing we can do is understanding these things, we can sort of design an optimal system where we can actually then put the membrane into an overall stack simulation and understand how we can improve the performance of this material, of these systems. And we see that the best ways to sort of go from the commercial bipolar membrane system that we've been working with Aowen to a more optimal one be to improve the catalyst layer to eliminate that kinetic overpotential, and as well as introduce some sort of way of shearing bubbles off the surface with flow-induced bubble removal. And importantly, the thermal process is about 175 kilojoules per mole. With this optimized BPM, we think that we could get this process to under 100 kilojoules per mole per membrane. And so this could be a really interesting way to replace thermal calcination. The last story I'm going to talk about is this work I did on bicarbonate electrolysis. So not just carbon capture, but also converting the captured carbon into something valuable. And so this process basically relies on a lot of the principles that I talked about before. You have this acid that liberates the CO2 from our carbonate solution. But what we do here is instead of just letting that CO2 off gas and capturing it there, we put an electrode directly next to the surface of that bipolar membrane that contains a silver catalyst. And then so when we liberate the CO2, that CO2 reacts directly at the catalyst and forms syngas, a very value-added industrial product. And this was work that we did with Curtis Berlin-Getz group at UBC. Was trying to really understand the system of not just carbon capture, but also sequential conversion of the captured and desorbed carbon within a single system. And so you get this really nice net reaction where you can take a carbon capture sorbent and then using the bipolar membrane water dissociation and that silver catalyst to directly go to CO gas, which is a very value added product for downstream Fischer-Tropsch making plastics and fuels. And so one of the things we wanted to do is, again, understand how to engineer these systems, understand how to optimize these systems. And so we were able to work with Eric Lees at the University of British Columbia to model his bicarbonate electrolyzer. And so you can see it here. It's exactly sort of as I described it, as you would expect. You have this bipolar membrane. And then on either side of the bipolar membrane, you have porous electrodes that sort of directly sandwich that bipolar membrane. You flow potassium carbonate on one side. That allows you to generate the CO when the bicarbonate reacts at that cation exchange layer, liberates the CO2, forms the CO on the silver foam, and that CO then can get taken out. On your anode side, you're just doing oxygen evolution. So that's just your counter reaction to balance that bicarbonate electrolysis. And so, you can see here, you can zoom into this, and this is the modeling domain that we chose to do, which was we were really only interested in this system in sort of the dynamics between what's happening in the cation exchange layer where our CO2 is being desorbed and what's happening within that porous electrode where our reaction is happening. And with this sort of simplified model of the membrane and the porous electrode, we can actually get really good agreement between what's happening, again, in our model, in our simulation, and what happens in the experiment. You can see here that as I increase the current density, my CO selectivity decreases, and my yield sort of has this sort of local optima with respect to the partial current density. Ultimately, we want to be able to get to a point where we have very high yields and high selectivities to our value-added product of CO. And so again, we're able to use this model to sort of understand how to improve the performance of these devices. And what we see is that the model reveals that the mass transfer of CO2 and bicarbonate within the silver foam are the primary dictators of the selectivity of this reaction. So we find that if you can control and improve that mass transfer, for instance, by increasing the porosity of the silver or decreasing the thickness of that foam, you can dramatically improve the selectivity of CO to your value-added product. And so ultimately, this led us to really understand that when we want to improve these bicarbonate electrolyzers, modulating the properties of these silver foams, we're going to be really important to improve performance by tailoring the mass transfer of this bicarbonate delivery and the CO production within that complex porous electrode. And so finally, to conclude, I really think that bipolar membranes are going to be key materials in this sustainable future that we're all working towards. They possess really interesting emerging properties that make them greater than the sum of their parts. You've seen that here in terms of their ability to generate acid and base from electric applied voltage, and then to use that acid and base to perform these interesting alternatives to the calcination reaction, both in the context of capturing carbon and then also sequential capture and conversion. There are some really interesting physicochemical limitations of bipolar membranes that we didn't have a chance to talk about today. For instance, how water transports in these materials is a really emerging area of study, and something that I and my group will continue to work on at NYU. And finally, I hope that you've seen that we can use these materials to enable sustainable alternatives to establish thermal processes that could potentially have reduced energy intensity. And so to conclude, I just want to say, we talked today about carbon capture, but bipolar membranes will be everywhere across industrial chemistry. And we're looking forward to continue to work on these exciting materials, and also looking forward to hear about what AON's been doing on bipolar membranes on the side of industry. So thanks.
That's fantastic, Justin. Thank you so much for the talk. I think we'll go right to Eowyn's talk and then take questions for both of you together at the end, if that's okay.
That's great.
So thank you so much. So Eowyn, if you want to start sharing screen, and while everyone is taking a sip of their cup of coffee, Simon put in the chat some of the links for the DC-MUSE consortium, the LinkedIn page, the YouTube page, where all of these seminars will be hosted, and the webinar page of DC-MUSE that shows past speakers and upcoming events. The next one will be in February. So thanks again for putting those in chat, Simon, and Eowyn, the floor is yours.
Great. Thanks so much, Wilson. And thanks, Justin, for the wonderful talk. It's a perfect lead-in. I think these are great, obviously, go hand in hand. And I'm glad that Justin was able to kind of go into some of the fundamental chemistry. I'm going to talk a bit more high level about how we've been actually using bipolar membranes for our capture systems. So yeah, as Wilson shared, I work at Captura, where we've been working on direct ocean capture of carbon. And so, as you likely know, there are many different ways to capture carbon, a lot of which are direct air capture based, as Justin spoke about. But you can also utilize the ocean, which is one of our greatest resources. So about 30% of anthropogenic CO2 emissions are absorbed by the ocean. And so any amount of CO2 that we can remove from the ocean and sequester and or utilize, that same amount of CO2, or the CO2 then equilibrates and is pulled down into the ocean. So that is the main focus of what Captura is working on. And we're doing that via electrochemical pH swings, as Justin spoke about, and I'll get more into that shortly. And then finally, in doing this, we've developed an excellent bipolar membrane electrodialysis system, and we're also looking into multiple other applications in which this system can be useful. And so I'll talk about that at the end of my presentation, some of these, that and more that's on the presentation there. So getting into a bit more here on Captura's specific system. So as I mentioned, there's an equilibrium that exists between the atmosphere and the ocean when it comes to CO2. And so when the CO2 is absorbed into the ocean, it then reacts to form carbonate and bicarbonate, and depending on the pH, it exists in different form. What Captura does is we pull in the ocean water. We then are able to extract the CO2 and output a pure stream of CO2 and a CO2 depleted stream of ocean water back into the ocean. So we can directly measure the exact amount of CO2 that we're capturing using this methodology. We have no additional inputs into the system other than ocean water and renewable electricity, and the only outputs are the CO2 depleted ocean water and the CO2 that we've captured. So getting a little bit more into the chemistry I just mentioned, when the CO2 is dissolved into the ocean, it reacts to form bicarbonate and carbonate ion species. Depending on the pH, you can shift what the prominent species is to make it easier to extract the CO2 from the ocean. So we utilize this pH swing and shift the pH to the lower end of the spectrum so that we have most of the carbon in the form of dissolved CO2. This allows us to then strip the CO2 out just using simple vacuum systems and then recombine our acid and base. So getting into the actual electrochemistry of this, Justin did a great job explaining how bipolar membranes work. So I don't have all of those details here, but now that you understand that chemistry, I can explain how you can put that together into a larger stack and system. So here you see repeating units between your anode and cathode of bipolar membrane, and then individual anion and cation exchange membranes. So the bipolar membrane, as Justin explained, is what allows you to dissociate the water into your H plus and OH minus. Once you've done this, you want to make sure that you can trap those and that they don't recombine. And so that's why we use these additional membranes, the AEM and the CM, which allow us to both trap those and do salt splitting within that channel or salt dialization. And then we create HCl and NaOH and in two separate streams. So when you put this into the overall system I shared, again, we pull in that ocean water. We actually are able to keep most of the ocean water going straight through the main part of our process and only divert about less than 1% of the ocean water through this electrodialysis unit. The water that goes through the electrolysis unit has to be softened and filtered to prevent fouling of the membranes. So we want to avoid having to do extensive softening in all of the ocean water that we're pulling through our system. So we soften about 1% of it, run that through our electrodialysis system, create the acid and base as just described. The acid is then sent through our vacuum system where the CO2 is removed, and then the acid is recombined with the base stream and returned to the ocean. So quickly, before I get into a bit more of the membrane development, I just wanted to share some images here of the pilot plants that we've developed so far. So currently we have a 100-ton CO2 per year pilot plant at the Port of Los Angeles on the barge that you see in the image there. That's been operational for over a year now, almost 2 years. And we now also have a kiloton pilot plant in Kona, Hawaii, that was commissioned earlier this year and has been fully operational throughout this year. So, getting a bit more into membranes and electrodialysis, I kind of already reviewed this stack idea, but as I mentioned before, we have a bipolar membrane, a cation exchange membrane, and an anion exchange membrane that allow us to make acid and base from our saltwater feed. When you take this unit, we call that a triplet, and then you can repeat that triplet as many times as makes sense in between your two end electrodes. So the image on the bottom here is an example of one of our pilot stacks that's currently operating at this Port of LA pilot plant I mentioned. And this one in this example has 100 repeating triplets. So the dark area that you see in the middle between the two white plates here, those are actually the gaskets that then go in between each layer of membrane to create this repetition. And therefore you minimize the voltage needed for your end reactions across, in this case, 100 different channels of acid and base. So you're able to create more acid and base for a lower energy input need. So getting now into what Captura has really been working on in the bipolar membrane and electrodialysis world. So Captura has actually started from the ground up in that we make all of our own polymers and membranes, and then we do the material testing and we build stacks and systems. So we have started producing polymers when I first started working at Captura at the grams scale and making tiny little sheets of membrane. We've now been able to scale this up to the much more industrial process at our facility in California. So the image you see here is one of our larger reactors. We have 20 to 50 liter reactors now to produce these polymers. This production then allows us to cast significant quantities of membranes. So we are now also casting our membrane at a roll-to-roll scale. I'll get into that a little bit more in a moment. And then we have significant materials testing capability that allow us to iterate really quickly on our membranes. And we also have developed our own stacks and systems that allow us to integrate our membranes and optimize the process even further based on the flow channels and the design within the stack itself. So this is a bit of a flow diagram here of kind of the polymer to membrane. So as I mentioned, we started at a much smaller scale. It's not actually even imaged here, just very small few milliliter bottles. Then we moved up to, five-ish liter reactor. Now we're at 20 to 50 liter reactors, as you see here. Once we make the polymer for the membrane, then we dry the polymer and you end up with this kind of powder that you see here. We then take that powder, and one of the really key aspects in casting your own membrane is developing your casting solution. So a lot of work has gone into developing what's actually in this little bottle. Obviously, we develop it at a much larger scale than what's just in that bottle there. But the solvents and ratios that are used in this casting solution are really critical when it comes to developing how the end product of the membrane turns out, especially when it comes to a multi-layered membrane like the bipolar membrane. We then use this casting solution to do initially in-house casting. So the image here using a doctor blade on a casting table, you simply put down your casting solution and the blade moves across the surface and casts a sheet of membrane. You then put this in a dryer and dry it to the appropriate amount, and then you end up with a sheet as depicted in this lovely image with the green fingernails. So this is what our membranes look like. If you didn't know any better, it would look like just a sheet of plastic. But they actually do amazing work in our electrodialysis stacks. We've now taken this process and scaled it up to a roll-to-roll production of our membranes. So we've been able to take all the learnings from our hand cast membranes and produce membranes at this roll scale that you see here. And just a quick imagery of what this looks like. This is just a random image, not the exact one that we're working with, but the concept here is that you actually start with a roll on one side of your system. The roll would be some sort of inert backing material. You then roll this through you typically is called a slot die. It's similar to the casting bar, but it actually holds the solution within it. You're able to then extrude the solution onto your backing material as your backer moves through the system. It then runs through the oven and rolls back onto a roll at the end of the system. For the bipolar membrane, we're able to then repeat this 3 times for each layer of the membrane. And really perfecting each of these steps has been a really critical aspect in the development of our membranes, and is not a simple task to move from, layering membranes and hand casting membranes to be able to directly roll to roll cast. And so this has been a kind of a really big and exciting step that we're now able to produce our membranes in this way after great trial and error. So again, I mentioned earlier, one of the ways that we're also able to do this development is through great feedback in our characterization abilities. So one of my main roles at Captura has been to develop our characterization lab. And so we've built out extensive number of testing stations so that anytime we create any new iteration of these bipolar membranes or other types of ion exchange membranes, we can do immediate testing and give that feedback. I think I forgot to mention earlier, our roll-to-roll casting is done with a US-based manufacturing partner at this point. They've been a great partner with us, and they were actually allowed us to even set up one of our testing stations on site at their facility so that we can iterate and test while we're casting the membranes there. But in our California facility, we have, again, extensive number of these test stations. So to get a bit more into the detail of what we really pinpoint when we're doing characterization, we really care, the big factors that we care about are the voltage across the membrane and the efficiency of that membrane. And these are going to end up leading to what the overall energy that goes into the system will be. So we have these cells that are developed to probe just the voltage across the bipolar membrane, and then just the efficiency that the bipolar membrane itself has. So for the voltage, we use Lug-in capillaries and reference electrodes, which allow us to measure voltage directly across the bipolar membrane, and we isolate those channels using AEMs and CEMs so that we don't have any interference from our end electrode reactions. And so we can measure, a range of currents and understand what the voltage across the membrane is. Next, we also do, as I mentioned, ferritic efficiency. And for these measurements, we're mainly measuring the output of acid or base that we're creating. So we can calculate based on the current, the expected concentration of our acid and base, and then measure what we actually get, and that tells us the efficiency. For these cells, we've actually added an additional channel. We want to make sure that we collect all acid, or in the case if we're looking at the base, all base that is produced by this membrane, and we're not, again, losing any due to these leakage potentials across the AEM and CEM. Again, this is to evaluate just what the bipolar membrane itself is doing. When we look at the full stack, we actually look at the system more holistically. So from these numbers, we're able to produce the plots you see here. So again, we scan a range of current densities and we measure the voltage across the bipolar membrane. Captura's bipolar membrane that's cast in this roll-to-roll fashion has been able to achieve excitingly low voltages. And we're actually currently, when testing multiple other commercial membranes in our same system, we achieve the lowest voltages that we have observed. Additionally, we use some of these cells to run voltage stability tests. So this example here is one of our membranes run for 1,000 hours, holding the same 1,000 hours at 800 amps per meter squared, and it holds the same voltage of around 1 volt for this entire run. Again, we measure many other things as well. So we do lots of thickness, temperature stability, pH stability type measurements. We also do mechanical testing. And we have full technical data sheets that are even more extensive than the table listed here that that describe all of the characteristics of our membranes. So because we have to develop both cation and anion exchange membranes for our bipolar membrane, we actually have utilized the cation exchange layer polymers, and we are producing our own cation exchange membranes as well. And so we do similar types of characterization to understand our cation exchange membranes. And so the first thing that we do is we measure what we call hydroxide blocking efficiency. So in this case, we've developed similar to the cells you just saw, but we've rearranged them slightly, and we flow base on one side and salt on the other, because this is the condition that the membrane will see in that full stack that I shared earlier. And then we measure the amount of hydroxide that leaks across that CEM into the salt channel. And this is a key characteristic when it comes to these full stacks. Similarly, we do these, we don't actually currently make our own anion exchange membranes, but for any commercial anion exchange membranes that we work with, we do a similar process with acid on one side and salt on the other, and we measure the acid leakage across that anion exchange membrane. And then we also, the other key aspect for an CEM or an AEM is just the resistance directly across the membrane. So we've put together these cells that are just simply electrodes with some gaskets and flow solution on either side, and do an EIS measurement to measure resistance in these across these membranes. So we can produce similar tables here. So if you take that area-specific resistance and you multiply it out across multiple different current densities, you can see what the voltage characteristics would be. So basically what the voltage that that individual membrane will contribute to your overall stack will be. And again, you can see here, Capture has been able to develop a very conductive cation exchange membrane option. And again, it performs, as far as the resistance, it's improved over other commercial membranes that we've worked with. For the stability in these cases, we typically do stability measurements by soaking the membrane for extended periods of time in whatever solution condition it will see and temperature that it will see, and then taking repeated measurements of the resistance and the blocking efficiency. And again, here this test ran for over 1,500 hours and remained stable in the efficiency and the resistance as well. And similarly, we do additional measurements, thickness, temperature, all of that good stuff. So once we have those membranes developed and characterized, we put them into our stacks. Now, I'm not going to get a ton into this stack build and design today because this is not my main focus at Captura, but I did want to share what we have developed here. So as I mentioned before, Captura has actually designed our own stacks, and that specifically includes the flow channel within the gasket. So each of the dark layers that you see again in each of these stacks is a gasket, and if you were to turn it on its side, you would actually see a specific channel that the solution flows through, and it flows past each of the membranes. And the design of that channel is really critical for improved efficiency within the full stack. So if you were to say take all commercially available membranes and put them inside the stack, we would actually have improved efficiency over a commercial stack already without the replacement of our membranes, which is really exciting progress for us. So the first stack that we developed was a lab scale stack. So that's the first image you see here, 8 by 20 centimeters. And typically we test these with 6 triplets. We have, I believe, 5 of these now on site. So we're able to iterate a lot at this scale, as well as run stability measurements at this scale for the full stack stability. We then have a pilot scale, which operates at our pilot facility in Alta Sea that allows us to test membranes on our actual ocean water system at a slightly larger scale. And then finally, we've just finished commissioning our full scale stack. This is being tested in our Pasadena facility and has dimensions of 50 by 140 centimeters. That's this final image here. The image here, I believe, has 100 cell triplets in there. And this is what we'll actually use in full direct ocean capture systems. We would take this unit you see here and repeat this unit as many times as needed, depending on the size of the ocean capture system. This is some stability data that was produced from one of our stacks. So this is now looking at the voltage per triplet as opposed to the voltage just across a single membrane. And again, we're able to run long-term stability measurements on these lab scale membranes or lab scale stacks. And this helps us understand what the overall energy that needs for producing acid and base in our system will be. And a good comparison here, so if you look at our voltage and our efficiency, we're able to achieve about 1.2 kilowatt hours per kilogram of sodium hydroxide, which is a pretty industry standard way of measuring their energy needs. And if you compare this to the standard way that sodium hydroxide is produced, which is called chloralkali process, we're actually over half, we're less than half the energy needed for this process, and we produce acid at the same time that we're producing the base. So what this means is this is actually a really exciting way, industrial way to produce acid and base from a salt stream. And I'm going to get into that more in a moment, but the last images I want to share here are just some exciting images from the recent stacking of our full-scale stack, which is a really big progress point for us at Captura. So as I mentioned, we are able to make acid and base very efficiently with our stacks and our membranes. So then we recently have been thinking, well, where else could this potentially be useful? And we're starting to branch into actually looking to sell our membranes and electrodialysis products into other fields. And some of those main areas that we're looking at, one is long duration energy storage. So this is where you actually run the electrodialysis in both directions. Another is mineral recovery, water treatment, and direct air capture. I'll get into these now in a little bit more detail. So as I mentioned, the first one is long duration energy storage. So everything I've been talking to until this point has been what's called reverse bias, meaning you feed in a salt solution and you produce acid and base. But you can actually run your electrodialysis stack in the opposite direction. You can feed in acid and base, make salt, and it actually produces electrons. So you could use this as a battery where you go in both directions and you store your energy in the form of acid and base. So this is one area where we have been talking to other industry partners in interest of using our membranes and stacks for this application. We're also looking at how our membranes and stacks can be used in lithium extraction markets. So it's a very complicated and extensive process to extract lithium from brines. And our stacks would just be one component of this, but we believe that it could be a really compelling component considering that these processes need a significant amount of acid and base throughout the process. And we're able to provide that in a fairly cheap fashion. So the two areas in which we can really plug in the electrodialysis stack here, one is actually utilizing the brine stream to make an acid and base, which then can be used, the acid would be used to regenerate their sorbent materials. And the base then could be used in multiple other parts of the process, or we could combine this with this other option, which would be to actually use our electrodialysis system to convert the lithium chloride into a more useful end product of lithium hydroxide. So those are some of the two, just briefly going over those two applications in the lithium extraction world. Another exciting opportunity is in desalination or water treatment in general. And so in desal, they typically, they produce potable water, but then they also have a brine stream that comes out of the RO systems that they're using. We are able to use our bipolar ED to treat that brine, produce acid and base, which can then be utilized in multiple different aspects of the desal plant or other types of water treatment plants. So this is helping really utilize what would be a waste stream and then create useful products that can be reused within the product and within the process and create a circular system. And finally, I think Justin already really touched on this, but not only can we use our electrodialysis stacks for direct ocean capture, but they can also be applied to direct air capture for sorbent regeneration in replacing those thermal reactions that Justin spoke about in his presentation. So I won't go into that in too much more detail, but that's also an area that Captura is currently working with other companies that are doing direct air capture and who are interested in utilizing our electrodialysis systems. And I think that's all I've got. So thanks so much. And I hope that was interesting.
Super interesting, Awen. Thank you so much. And thank you again, Justin. These were absolutely two fantastic presentations that together, I think, built a really incredible story from basic science, fundamental understanding up into, pilot scale facilities. So thank you both so much for your time on this. I think we can open the floor for questions. I see there's a few in chat that are popping up. I'm happy to read the questions out, but if people want to ask them themselves, the floor is open. So the first question in chat is from Ahmad. Ahmad, would you like to ask your question, or I can read the question for you if you'd like? I don't see.
Yeah, thank you. I have thank you first of all for both of these amazing presentations. And so I have a question from Justin. So one of his slide, he mentioned that the porosity can do the amazing work. So can we actually achieve 0.9 porosity? Because in my opinion, 0.4 is for fixed bed porosity, and then afterwards it's a fluidized bed. So can you explain a little bit more on this? Thank you.
Yeah. So so one thing is in porous electrode systems, you can definitely just you can achieve very high porosities. There are some solid electrolyte fuel cell systems that have porous electrodes, in the 50 to 80% porosity range. I agree 90% is maybe a little high, but this is more just a computational analysis, right? If we could get to 90%, what would that lead to in terms of the selectivity enhancement? I think there are definitely ways, especially with electrodes, in terms of like etching and increasing active area in those ways, that you can get to very high porosity electrodes. Is something that's been developed a lot for GDEs. So I think it's something to consider. I don't know if 90% is necessarily going to be a super feasible value, but I think it was more so just for the demonstration of the sensitivity. I think though 50 to 80% is definitely well within reason for something that you could achieve for a porous electrode.
Yeah. Thank you. I appreciate it. Yeah.
Thanks for the question, Ahmad. The next question in chat is from Matt. If you want to ask your question, let me see if Matt is in chat. Are you there, Matt? All right, I can ask Matt's question for him then. It's a really great question. So I think this goes more for Awen and the applications for seawater. Matt's asking, what impact do seawater constituents other than sodium chloride have on the electrodialysis process, particularly regarding cell efficiency, membrane durability? And then he also asks, what is the maximum continuous operating time for which stack performance has been successfully demonstrated with seawater? So that's a lot there, Awen. So basically, how do you deal with very messy, dilute seawater when you need to do really, well-defined chemistry?
Yeah, great question. So as I mentioned, we mainly don't deal with it is really the answer. We use a lot of pretreatment steps before the ocean water goes into the electrodialysis system. If you were to feed ocean water directly into the electrodialysis system, it would probably kill it within days. And that's mainly due to fouling of things like calcium and magnesium in your base channel scaling onto your membranes, which in those cases can be cleaned with acid cleaning steps, but ideally we don't want to be doing that frequently. So yeah, this is why we've kind of designed the process so that we can send a small percent of the ocean water, only the small percent through the solution, so we can just treat that. So we treat that for the hardness, and we also send it through nanofiltration. And by the time it goes into the stack, it's almost just like a sodium chloride solution.
That's awesome, and I think that's a good in this consortium for chemical manufacturing. That's how a lot of chemical process industry works. It's not one system that gives you one input, gives you all your output pure. You have lots of these individual steps that are very highly optimized efficiency, and I think this is a great learning that is translating from the chemical industry.
Yeah. Also, I think to answer the end part of that, once we treat it, we've run it for 3,000 to 4,000 hours. But that's mainly just because that's how long we've had our membranes on hand. Those tests are continuing.
That's awesome. I see we have one more question in chat or a hand up from Mehran. Would you like to ask your question?
Yes, thank you for the really nice presentations, both of you, Irvin and Justin. My question goes to Irvin. I think you mentioned that you use nanofiltration for the softening process, but have you tested using the base that you produced, so the sodium hydroxide, to soften the water? And is it enough, or do you need it later for the basically neutralization of the acidic seawater? Have you done anything in that regard or no?
Yeah, great question. We absolutely have. We have kind of two different systems that we're currently developed. Actually, we have both of these systems at our Port of Los Angeles pilot, so we can test both of them. One is mainly focused on nanofiltration, like I mentioned, and the other is exactly what you said. We use our base to crash out the calcium and magnesium and hardness in that. And then we actually then use that as well as the rest of our base when we recombine everything and put it back in the ocean, because we want to make sure that the magnesium and the calcium and all of the hardness is actually still in the ocean water. We don't want to affect the ocean water in any way. So we actually have done some studies to see how quickly those elements recombine into our ocean water when we recombine the acid and base streams. So our goal is to basically not actually leave anything out once we return the ocean water.
Okay, thank you.
Sure.
We have a couple of minutes left for more questions, and if there's nothing in chat, I have a question for Justin. I guess, but before I go, I see it is my absolute pleasure to call on Hussein Almajed. Please, Hussein, ask your question.
Thanks, Ewan and Justin, for this great talk. I think this really provides the full picture from the fundamentals to kind of the actual world, right? So my question is to Ewan. You showed kind of those operational time figures, and I'm wondering if, I know in your recent work you showed this stability tests for 4 centimeters squared. Are these applied to the 200 centimeter scale?
Yeah, great question. So the initial, I showed kind of two different stability tests. The first one I showed when I was talking about probing just the individual membranes themselves, that's still around the 4 centimeter squared area. Then the later stability test that I showed with regards to the stacks, those are the lab scale stacks that I mentioned. So that would be 6 repeating units of around, I think it's 8 by 20 centimeter size membranes. So yeah, significantly more area there, helping really prove out that the membranes will work at larger than 4 centimeters squared. Yeah.
This is really exciting. And then maybe another follow-up question. In these systems, there would be especially for seawater, there will be some kind of capex trade-off, you can use more membranes to extract CO2 from seawater. So I'm wondering if the cost of the BPM on your roll-to-roll manufacturing process is comparable with what already exists today? And if not, or if so, have you like found like some other designs, the BPM unit that can minimize this cost, and like the two membrane cell, the doublet, if you will? I know you guys have done some work around that BPM design earlier.
Yeah, also a great question. I tried not to talk too much about cost because I wasn't trying to steer away from being a sales pitch. But it's a good question, and it's actually something that we've worked really hard on. And one of the kind of driving reasons that we decided to develop all of our own polymer and in-house, and all of our production mainly in-house or with our partner, is to really drive down the costs of this, because we saw that was really the only way that we were going to be able to make this a reality. And so at this point, yes, the costs of our membrane are less than half of typical costs that you see for bipolar membranes on the market. If you're more interested in diving into any of that and also want to try any of our membranes and talk more about that, feel free to reach out. But
No, that's yeah. No,
yeah, but yeah, we're really sensitive to that. But there is always a trade-off, right? As you mentioned. So one thing we're always analyzing is, our membranes also work at higher current densities than your typical industry standard is around only like 400 to 500 amps per meter squared. Whereas we can operate up to, like, a lot of our tests are at 800. We have operated up to 2000. Well, really, we've run them even further than that, but stability wise, we typically operate around 800. And that again is based on the trade-off of the energy versus capex, or OpEx versus capex.
Yeah, no, that's a great. Thank you so much. I just want to share one final thought that I think these tests are proving that your system is really well designed for direct air capture, which is really also interesting. I'm excited to hear more about that or see more advancements about that in the future. Great job.
Thanks. We're excited too.
Thanks, Hussein. I see the next person that had their hand up is Sawyer Paulson, if you'd like to ask your question.
Hi, yeah. I just want to ask a question about the ratio of seawater that you intake compared to what's just passed straight through. So the amount that's put into the BPMED units. What was the thought process between the intake percentage of being less than 1%? And how does that relate to the efficiency of the system?
The process behind that would be basically what's the smallest amount that we possibly can pre-treat, because we have to pre-treat anything that goes through electrodialysis, and still get our overall ocean water to a pH that will push all of the carbon to being in the form of dissolved CO2. So basically, if you think about, okay, so we have around 1%, and then that 1% we take to a pH of 1, and then we drip that into the rest of our solution. That allows us to get, if remember that chart early on in my presentation, it's called the Bajorem plot. That shows you that you only really need to get to a pH of 4, and then below that, 4 and below, pretty much all of your carbon is in the form of dissolved CO2. So as long as we get the small amount to a pH of around 1, then that's enough to get the rest of the system to below 4.
All right, thank you.
Thank you, Sawyer. And I think we have time to squeeze in one more question from Andre.
Yeah. Hi. Thanks for a great talk, Justin and Owen. It was really, really good. And this is an example of seeing how you can have something that's on the lab scale development with the fundamental science, and then you can also see how something can be expanded and bridged out. I had a quick question, I guess kind of for both of you guys, as looking at a technology that's developed in the lab and then trending to a marketplace and for applications. How do you address the challenge in terms of scale up? Because that seems like a very big challenge. I mean, I think from my experience in the fuel cell industry, moving from a single cell to single cell MBA to like the several stacks, and you have like several complications that are flowing in there. How did you guys develop that, or think about that, or develop the expertise to put that together?
I'll let Eowyn. I'll say that on the fundamental science side, I think that I'm really interested in, and this is something that like my PI at Berkeley, Adam's group, is very interested in, modeling systems as full stacks, thinking about energy losses in all of these different layers. And I think that has helped at least us think about how to design these systems, like having a really good physics-based approach, being able to rationally design these systems from an engineering perspective is really important.
Yeah, I think that's a great point. I think the kind of the perspective as he ended on is a great way to put it. I mean, the easiest thing to say is bring together a great team, which is honestly what Captura did, is what I would say. We brought in people that had done this before, and people that had worked in, electrolysis stacks in other industries, and also people that had worked in polymer production in other industries, and then helped a lot in the scale up, but also just thinking about, starting from the very beginning and saying, okay, if we make this at the small scale in a way that's not scalable, that's never going to work. So we kind of started at the small scale, but made sure that the way that we were casting the membrane would reasonably well translate to a way that we knew we could produce it at the large scale. Similarly, I believe we designed the stacks from the top down. So the full size stack, although we only built that recently, that was designed first, and then the smaller stacks were modeled after that.
Thank you so much. It's very good.
And I think we're just at or over time. Thank you again to our speakers, Justin and Eowyn. Those are really fantastic talks. Thanks everybody for showing up and asking so many great questions. I think based on the amount of people we had, the breadth of questions we had, this is clearly an exciting topic with a lot of room to grow for both people in academia and industry. So thanks everybody.